Hi, welcome back. So, I guess today is another session about MapReduce. It's not a session, it's just me learning stuff, right? So, yes, if you haven't watched the previous video, which I haven't uploaded yet, I mean, I'm not even uploading anything. I just record for the sake of it. I just enjoy recording the video. But yeah, in the last part, we had a section where we learned, where at least I learned about MapReduce. Okay, 1 second. Yeah, now it's easier to talk. Okay, so where I learned about mostly about MapReduce, I will give a bit of context what it is and what's the introduction. But yeah, we finished also the introduction, and now we are coming to the programming model, which is the second part. Hopefully, in this video, I will cover that up. I probably want to understand like how this actually works because theoretically MapReduce seems pretty easy, and that's the point, right, of MapReduce. Anyways, here's a quick overview of what MapReduce is, and let me just zoom it. Yeah, okay. So basically, MapReduce, I would say, is an abstraction. It's pretty much a programming model or distributed system model, where we have an abstraction which takes some sort of key value pair. Then we provided a map function, which basically does some which does computation on it and produces an intermediate set of key value pairs, and those intermediate set of key value pairs are ran through a reduce function which is also provided by the user, and they take the same intermediate key and then produces a value out of it. So this is what MapReduce is, but that's not the coolest part. The coolest part is that uh, meanwhile the user only need to provide map and reduce function. Internally, the abstraction take care of everything on a distributed system. So we will have multiple nodes and excuse me. So we will have multiple nodes, and each of the computation will be parallelized onto the distributed system, distributed nodes, and everything like fault tolerance, also parallelism and consistency, all those kind of stuff will be taken care internally by the MapReduce algorithm programming model, I would say. And yeah, so the user just need to only think about what's the map function, what's the reduce function, and everything regarding the distribution stuff and distributed system. The hard part is essentially taken care by the algorithm, by the abstraction itself. So that what it map reduces, and that's what the abstract and pretty much introduction was in a very small sentence. So yeah, now let's coming back to the programming model. Okay, so programming model. So as you might know that I'm not going to teach anything here. Like it's just me trying to understand what this paper is all about. So uh, I will go through the each and every word of this programming paper. Try to understand. Try to say out loud what's my thinking process is, and that's all there is to it. It's a pretty dang boring video, I can tell you that, but it is what it is. So the computation model takes a set of input key value pairs and produces a set of output key value pairs. The user of the MapReduce function expresses the computation as two functions, map and reduce. Map is written by the user, takes input programmer input pair and produces the intermediate set of values. The map the MapReduce function libraries to group together all the intermediate associated with the same identity key and passes them to the reduce function. Okay, so I think that's similar to what I had said in the introduction video. Let me just go through this one quickly as well. The reduce function also written by the user accepts an intermediate key I and set of value that here the it merges to of these values to be able to form a small typically just 1 0. Yeah. Hmm. Okay, I think the last one line is interesting. The intermediate values are supplied to the user's reduce function via iterator. Okay, this allows us to handle list of values that are too large to fit in memory. Yeah. Okay, so essentially what it's saying is the exact thing I have said it here. So this diagram is pretty much what has been said here. So map is written by user, which takes an input value pair, produces an intermediate set of values. These intermediate set of values now are thrown at reduce, which is also written by user, and it takes all the same intermediate key values and merges them together to form a smaller value. It could be either zero value or it could be an output. No, not zero value. It could be a zero. It could be output. What I was saying, basically, the reduce function takes the intermediate set of keys uh, and merges them and could produce a output or not. Yeah. Okay, that was hard. So yeah, and typically just yeah, okay, that's what it said. Whether we can produce a single value or we can produce none value. And the intermediate, yeah. So now the question is, intermediate values are provided through an iterator, not rather than just loading the whole list, because loading the whole list will cause issue if the list is too big to be fit in memory. So we just provide an iterator and the reduce function run the iterator on it. Pretty easy stuff. Not easy, the hard part they have implemented, but pretty intuitive stuff, I would say. Mhm. Consider the problem of counting the numbers of occurrences of each word in a large collection of document. The user write a pseudocode following to. Okay, so the point is that we are trying to count the number of occurrences of each word in a large collection of document. So basically, we have a large collection of documents. Okay, so yeah, we have multiple documents, I guess, and then we want to count the number of occurrences of each word. Yeah, so we want to count whether a certain word has been encountered how many times in all these collection of documents. Okay, so essentially, if this would have been if this would have been a normal problem and it's not some distributed system problem, it would have been easy algorithm implementation, right? So considering that each of the documentation could be read in a string, I'm just talking in a very I would say very shallow manner. So that let's just say each document could be loaded in a string. We could iterate through the string for each word, load it in a hash map, and then count for the total number of occurrences of each word, and then we could do it for all the documents. So if this would have not been a real world problem and just a data structure algorithm problem, it would have been easier to do this, right? Just load everything in hash map is the answer essentially in every DSA problem, right? Okay, no. But anyways, right, you got the point. That essentially the algorithm itself is not that hard to write if this would have not been a Google scale problem. I mean, if this would have been my toy project, I would have never used MapReduce. I would just load everything in hash map. But yeah, that's why my personal project are not Google. Okay. Anyways, so we have map which takes the string, which takes the value. So key is essentially the document name, because yeah, for each document we want to get the document contents. Okay. So map is basically, so this is how this is how the user is going to use MapReduce. So map is a function which takes some key and value. That's what we know, right? From here, map essentially takes a key value pair. The key here would be document name and the value here is the document contents. Okay. For each word W in value. So yeah, but they essentially assuming that value is a word, we split it by something. Yeah. Okay. We essentially it's a string, we split it by some white space or whatever, right? And emit intermediate W for one. Okay. So yeah, we take word and okay. Emit intermediate could be some function which is pretty equivalent to what the hash map implementation where I said that take the hash map, plug the value it in, increase by one. whenever you encounter a certain word. So emit intermediate could be thought of as a hash map, but there's a one issue, right? So assuming that, okay, yeah, that's why it's not an, no, I was wrong. So hash map implementation can't be used here as an analogy, because map from this diagram provides an intermediate set of key value pairs, correct? So this emit intermediate needs to be providing for each key value multiple key value pairs. Okay, so now I'm getting it. So basically we take a document and take its content, and for each word we are going to emit key value pairs. Okay, so emit intermediate here would, the key would be a word and value with the number of occurrences we have found it, right? So let's just say we have a new word. I'm just trying to dig deep into what emit intermediate could be, right? There's no need to do that, but I just want to get a mental model of it. So if a new word is encountered, we emit a key with the new word, but its value is 1. If we encounter this another new word, it's the same thing. Emit a key with value of 1. If we encounter duplicate word, now we emit a key again with the value key as same but value as 1. Okay, since the key is same, I guess reduce will take it and count. Oh yeah, reduce will take it and sum all the same keys, sum all the values for the same keys. Yeah, but now the question arises is that key is a word. Yeah. Okay, yeah, and essentially key should be a word because we want to take these occurrences of all the keys of all the words, right? Okay, yeah, okay. So this is essentially just throwing out a key value pair. It's basically a dictionary or tuple or object, whatever to call it. Oh, that's interesting. Okay, so the hash map analogy would have been completely wrong, right, in that case, because we are not emitting nothing here, essentially. Yeah, but if we go by the hash map analogy, there's a plane going up here, so I'm just taking a little bit back. Okay, the plane is gone, more or less, so yeah. I was saying that for hash map solution, if we think by, I mean, yeah, hash map solution is not the right analogy here. But if I were forced to be making an analogy with hash map, what I would say is that pushing the key and value for the first time in hash map is equivalent to mapping function, and then whenever we push back another value, basically we increase the frequency of a key. That's reduce, but that then again this is a completely wrong analogy. If I were to force it, I would think it like that. But anyways, now I think I got the reduce function as well. So reduce takes a key and have an iterator value. Key is a word which is essentially emitted from here. Value is a list of counts. Okay, a list of count, what does that mean? I don't know. I don't know what does list of count means. Sorry. So int result equal to 0, yeah. For value in v, we take this, yeah, we just parse it into and add it, emit as string. Yeah, so that this is easy stuff. So okay, so yeah, that's okay. That's literally it is what it is. It is what it says. It's a list of count. So basically, for each key, we emit like 1 1 1 1. So the iterator is basically the list of the 1 1 1 1 1 1 1. How many times we had encountered it, and then we just take it and add it. We just go through each of the values, add them, and just emit them again. Interesting. So yeah, basically what it does is like map sends a key and one key one, basically let's just say word is the, so the comma one, the one, the one. We have a lot of these key value intermediate pairs, and before sending to reduce, we take the key and we take all the values, we combine them as list, but we don't load the whole list. We pass the iterator for the list, and yeah, okay, that makes sense. That makes sense. But yeah, they must have done some sort of internal optimization to ensure that there's, because I'm pretty sure that they don't load the whole list, right? That would cause the issue that is written here. So because sometimes the list would be too long and it would not be handled by in by basically RAM or in memory. So yeah, they must be the iterate. They must use iterator and they must optimize it in the same manner like they said. It's a list of count, but it's basically iterator over those values. So that's how I think of it as. So it's not exactly list of counts, I believe, because list of count in my knowledge should be. That's why I got confused, right? Because list of count essentially could be a very long list, right? And it must be hard for it to fit in memory for all the large use cases of Google. So I'm assuming for easy purposes it's list of counts, but it's technically iterator over the list of counts. Yeah, makes sense. That's all I can think of. I'm not sure. Maybe I'm completely wrong, but yeah, I don't think that's essentially as way they load up completely. It must be iterator. I mean, they said it's iterator. The map function emits each word plus an associated count of occurrences. Just one in this simple example, yeah. The reduce function sums all emitted value for a particular word. Okay. In addition, the user writes code to fill in MapReduce specification object with the name of the input and output files, an optional tuning parameter. Okay. Okay, let me read it again. In addition, the user writes code to fill in MapReduce specification object. Okay. So yeah, basically MapReduce SDK, they fill it. SDK with the names of the input and output files. Okay, and optional tuning parameters. Okay, that literally SDK stuff. SDK. The user then invokes the MapReduce function, passing it the specification object. The user then invokes the MapReduce function, passing it in the specification object. The user's code is linked together with a MapReduce library implemented in CPP. Appendix contains the, for example, yeah, maybe I will let. Yeah, I think I will probably take a look at it later. But essentially, it is what it says in this diagram again. Even though the previous pseudocode is written in terms of string and input, conceptually the map and reduce functions supplied by the user have associated two types. Map K1 V1 map. Yeah, so it's a list. I don't know, man. How could it be a list? I'm not sure. Okay. List K2 V2, yeah, list. That is the input key and value are drawn from a different domain for other than. Why is I big here? Okay, because that's the first word we are studying. Wait, we do that? In that is, I don't know. In the input keys and values are drawn from a different domain than output keys and values. Furthermore, the intermediate keys and values are from the same domain as the output key. Wait, what? So it's saying that intermediate key values are drawn from different domain. By drawn from different domain means that they. Okay, yeah. So they are saying that we supply the key value that we supply the key and value for input for the map from different domain, basically from different software, like yeah, basically different domain means from external, right? It's an external input that we provide. And they said that intermediate key values are from the same domain as the output key values, means basically we produce the intermediate key and the key from values from the reduce in the same domain, basically. Okay, so domain is basically just a system as a domain. So MapReduce function system is the domain. So when we say that we the in key values for the input for the map are provided from the output from the different domains, basically we are provided, let's just say this is the system and we are providing an external input. So we are saying that this input is from the different domain because this is outside the system. Okay. And okay, why I'm saying okay, I can just draw it in Excalibur. Why was I saying it? Yeah, I'm not sure. So let's just say this is the domain of yours. Let's make it large. Right, so this is your MapReduce domain, and we'll just make it MapReduce. Yeah, that's easy. So, and when if I have some input, so whenever we provide some input, it goes like this. Yeah, I need it. Now it's good. So this is the external input we are providing for so this is the input we are providing for the MapReduce domain. It should be MR, by the way. So this is the MR domain. Also I can, right, so we produce it to the map function. Map function internally produces, I guess, it produces some domain, right? Intermediate domain, I would say. Intermediate representation, intermediate domain, right? So it, oh no, it produces some internal, it produces a key value pair. Okay, yeah, okay, so it produces some intermediate key value pairs. So let's just denote it with small circles. Yeah, and since they are inside, still inside this domain only, this is inside the MapReduce, I would say MapReduce system. It's essentially inside the same domain, and if we run it on reduce again, yeah, okay, so if we run it on reduce again, it will reduce will provide us a value, right? It will provide us a value, and that value essentially is still inside the system. Obviously we will provide it to the outer system. It will be provided later to the outer system. Wait, what? Yeah, okay, so we will be providing it to outside system, but since the output was outputted by the system, by the reduce, and is still inside this, it still can be counted as it was in the system, right? I mean, I don't know how okay, let me recap it again what I'm saying. It's a little bit confusing to say. So essentially the MapReduce, let's just think of MapReduce as a system. So whatever inside that system can be said that it is inside the same domain as MapReduce. It's in the same domain. So we provide input from the outside and external system, obviously. So it's not from the MapReduce system. So essentially it's a external input, or it's from the outside domain. The map takes it, give it as some extra intermediate key values pair. Reduce takes it, works on it, and produces output. Obviously, since intermediates are inside obviously the MapReduce system, it's in the same domain. Reduce then essentially puts out a value. Now this value obviously will later be supplied to a outside system if required, but once it's been outputted, we can say that it is still conceptually inside the MapReduce system. Yep, and obviously later we can provide it, but yeah, the moment it get outputted, it's inside the MapReduce system. Providing it later to external system or not is the design decision by the business requirements. Okay, that was tough to explain. Oh, that was really tough to explain, I guess. Our C++ implementation passes string to and from the user defined function and leave it to the user code to convert. Yeah. Wait, what? Passes strings to and from the okay, yeah, so it says the same thing, that it says that we just our implementation uses key map and val reduce. I was saying map and reduce, but I said key and value instead. So yeah, it says that the implementation uses key and it's not key and value. It says that their implementation uses map and reduce from the user code and leave the internal everything to the MapReduce implementation. More examples. Here are the few simple example of interesting problem that can be expressed in MapReduce configuration. Yes, that's what we want. Distributed grep. Not sure how that works. The MapReduce function emits a line if it matches a supplied pattern. Yep. Okay, wait, what? The map function emits a line if it matches a supplied. Oh, so basically grep, for those who don't know, I am assuming everyone knows that grep grep basically takes a large string and takes out the part of certain pattern. That's essentially easy way to say it. So let's just say I send a long list of log, and I said that hey, grep it and just give me mm, just grep it and environment give me environment variable, right? So it will grep it, will take the supplied pattern and try to extract whatever matches that pattern in that log line. By the way, I haven't essentially actually, now that I think about it, I never implemented grep from scratch. So it will be an interesting project to actually work on. Yeah. Yeah, I think maybe I can work on grep as well. Like, I know essentially what grep is, but I never actually implemented it. Not even distributed one, like even a regular one, I never implemented. It must be based on some sort of regex, right? So we take a regex and we just parse a line. We just parse a line on that particular regex, and yeah, we basically essentially go through the line multiple times recursively, I guess, and take the regex. If we found a pattern, we emit it back. Yeah, it must be something like this. Yeah, I guess. Yeah, I can. I will probably do it. Yeah, that's a good. That's a good mini project to work on. The map function emits. Yeah, the reduce function is an identity function that just copies the supplied intermediate to the output. Yeah. Okay. So map takes it. Maps emit the line if it matches the supplied pattern. So if there's a supplied pattern, we matches it. Map throws it back. Map throws it to the intermediate key values. Basically, it shows the key value pair, and then reduce take it and it just essentially copy it to the output or your to command line interface or cout or whatever it is, and it takes all these values for a particular key, throw it out in your command line interface or whatever output we are using. Count of URL access frequency. The map function processes a log of the web page request and output URL1. The reduce function adds together all the count of the same element total count. Yeah, so it's basically saying that this is about how many times we have accessed a URL. So map takes all the web page logs, request logs, and whenever it sees a particular URL, it emits a event is not the right word. It emits a key value pair with URL one. Right. Reduce takes it and it just essentially sums up all the count for that particular URL. Easy peasy. It's like this is pretty similar to this. I mean, essentially, it's just taking a word, emitting it with one value, and then essentially reduce will crunch it and sum it up. Reverse web link graph. The map function output target source pair of each link to the target URL found in the source page name. Okay, I have to understand this one. So the map function outputs target or source pair of each link to a target URL found in the namespace. Okay, I think I got it. So let's look at it here. Let's just say we have this as source. I need to make this a little bit like this. Yeah, so that's source. If in the source we found a target link if in the source we found some sort of, why can't I write it here? Again, let's just leave. If I found some sort of target, not target, if I found some sort of target here, it, while map function, what it does, it outputs the value as target and source. So I'm just gonna take it, copy it, so it outputs this. Yeah. And obviously there will be multiple targets, so it will have multiple intermediate target and source key value pairs. The reduce function concatenates the list of all the sources URL as associated with given target URL and emit the pair of target localized. Yeah. So basically, reduce take all of this and give back us the target. Let me just copy this again. Essentially give back us the target and the list of sources. So basically it just concatenates it, right? So it gives us back this. So basically what we are here doing is we take a source, we take a lot of sources and we are trying to find that which, okay, so a lot of sources, like we have a lot of sources, and in each of the sources we will have some reference link to the target, right? So we will have some reference link to some other web page. So we are trying to find that how many, what are the, which web page, which what we are trying to find out is that particular web page was referenced by which other web page, right? Yeah, I think that's what we are trying to find out, right? Because let's just say, so we have a source URL, because I need to think. We have a source URL and we will have target. So a source URL is trying to refer that, hey, refer this below document for blah blah blah, and we will have multiple targets. Now we are going to take it, crunch it, and we are saying that, hey, for each of the target we have listed out all of the sources URL, that this we are pretty sure that for this target these are all the sources that have referred it. So yeah, that's what we're trying to find out. So basically we are saying that, okay, we have a lot of web pages and each of the web pages is referring to some other web page. So when we run MapReduce function on it, this essential use case implies that we will find it, we for each of the URL, for each of the web page, we are going to also give you which web page has linked, which web page was trying to refer this target URL in its own source code. Okay, essentially it was saying that, okay, we have this page and it's being referred in the following sources. Okay, I did it. This was the single most easy line to say that, hey, this is the web page and it is being referred by these many sources. That's it. It took me some time to actually convey that line. Yeah, it was hard. Reverse graph, yeah. Could have written it in easy manner, man. Could have written it in easy manner. Sometimes my English is so bad. Like sometimes I actually say the word, but people don't understand it because I talk too fast or my words are not clear enough. So yeah, I think this video also helped me actually mitigate this, because I'm now trying to regularly practice English consciously. So I guess I will be more fluent in coming future. Yeah, let's see how this goes. Term vector per host. A term vector summarizes the most important words that occur in a document or a set of map document as a list of words slash frequency. Okay. A term vector basically term vector summarizes that most. Okay. The term vector is basically summary of the most important word that has occurred in a document or in a collection of documents, and basically is represented in the format of word and the frequency that it have occurred. So it's essentially a little bit similar to this, but a different use case. Here we are trying to find the count of all the words. Here we say that it's the most important word. What is the criteria that says that hey, this is the most important word? I'm not sure. I'm not. The map function emits a host name term vector. Okay. Okay. Pair of each input document. This one's going to be hard, I can think. The map function reduce a host name. So host name is essentially, what is the host name exactly? Okay, I'm not sure. Term vector per host. The terms. Okay, so this is this. For each of the input document where host name is the extra. Okay, it literally says in the next line what host name is, and I was not reading it. The map function emits a host name and term vector pair for each of the input document where the host name is is extracted from the URL of the document. Okay, so we have a URL. Okay, let me get this straight. We have a URL. We are saying that okay, that URL is essentially the host name. Basically, URL we can just you in the URL we have different parts, and one of those part is the host name. So that's the host name we are talking about. Essentially, okay. So we have the host name and we have the term vector. Term vector is say that okay, it basically the term vector is the frequency or the number of times a word has been occurred, and that word has to be a most important word. Okay, so basically term vector is a list of all the most important words and their corresponding frequencies. That's what term vector is. So map function emits a host name and term vector. So I guess map vector probably map vector, what would it be taking in our input? It should be taking a host name, and yeah, it should be taking host name and it should be taking the content of the web page. Okay, and then we have the algorithm, we have the map function crunch on it, and we'll say that okay, I'm going to emit out intermediate key value pair as key with host name and value as the term vector, where term vector is the list of all the most important word and their corresponding frequency. Okay. The reduce function is passed all the reduce function is passed all per document term vectors for a given host. Yeah. Okay, so yeah, my first instinct towards that literally there will be a single function per host, there will be a single entry per host name, right? But no, that's not true, because a host, it's if it would have been URL, if the output was URL and term vector, then we could say that okay, there would be a single URL for each of the URL we will have term vector, right? Because URL pretty much is unique, and so yeah, so there won't be multiple instances of a URL and key value pairs, but hostname will have multiple intermediate key value pairs, because example is that we have google.com/document1, google.com/document2. Each of them will have different term vectors, but they will have the same key as google.com, which is the hostname. Mhm. The reduce function is passed all per document term vectors for a given host. It adds these term vectors together, throwing away infrequent terms, and then emitting a file. Okay, so basically what it takes all the term vectors, see that whatever the words that are infrequent, basically then again throwing the non-important words among all the document now, and it saves the important document. I guess it also sums up their frequency and then emitters back. So basically this is saying that for a single host we are trying to go through its all document, all URLs, and trying to find the most important words. So that's how MapReduce is used here, and that's a pretty unique, creative way to do it. Never thought that MapReduce could be used here as well. Okay, so now the next part is the inverted index. Okay, like I'm just too close my mic now, so it's like I'm giving ASMR. Okay, no, it's not ASMR, but yeah. Inverted index. The map function parses each document and emits a sequence of word and document ID. Pair. Okay, pairs. The reduce function accepts all the pairs for a given word. Oh my god, my eyes are hurting so much. My eyes. Let me. Okay, wait a second. Okay, I'm gonna complete this really quickly. Like my eyes are hurting. I have to do it. I have to do something of this thing. The reduce function accepts all pairs for a given word. Sort the corresponding document ID event out. Okay. The set of all output pairs form a simple inverted index. It's easy to augment this computation to keep track of word position. Wait, what? So like this one was easier, like this much is easier. We take document and for each word we emit document and the document ID. So yeah, this one is pretty, till here it's easy. So we take if we take a document, we say that okay, for each word we are going to emit the word and the document ID. The reduce take it, and it says that for each of the word I'm going to take all the IDs and convert them into list and sort them, right? So this is easy. The set of all output pairs form a simple inverted index. So the set of all pairs forms a simple inverted index means I think that for each of the output pair we have word and the list of all the documents in sorted order. Yeah, so it says that okay, basically we have a word and we essentially have now a very simple indexing system, right? Where we know that okay, this document contains this word, this document contains this word, and we have it in some sort of manner, some sort of sorted manner in which we can run the binary search upon, obviously. Not sure why they. I'm assuming that sorting has something to do with the searching, because in index we have to search, and if we have it sorted, binary search is the most efficient search here, but that's just my guess. That's just my DSA brain trying to DSA it out. It is easy to augment this computation to keep track of word positions. Now this is the line which I'm confused about. It is easy to augment this documentation to keep the word positions. Okay, I think I get it. Because we know that a word is being triggered by this document. A word is triggered by this document. So we essentially have word and all of the document that use that word. So it says that okay, since we have all the words and their corresponding document which were using that word in sorted manner, it is essentially easier to keep track of those words. Makes sense because we have all the indexes of the documents in sorted manner, and once it's sorted we can essentially, if we are required to do something, make an algorithm which is much more optimized and easy to work with rather than non-sorted document ID. I guess that's the only way I can think of. Maybe I will chat GPT it later, or maybe we'll chat GPT it now. That's also a good point. Wait, why can't I copy it? Why can't I copy it? Yeah. Okay, so it's a bit dense if you haven't seen the inverted index before. It is easy to augment this computation to keep track of word position. Instead of just recording which document contains the word, you can also record where in each document the word appears. What the hell, man? Wait, what? So I was just thinking like this, instead of recording. So I know that a word is now being used by this document and we have it in sorted manner. You can also record where in each document the word appears. Not sure how does that work. In basic version, map out our Word document reduce word doc id 2. That's correct. So far the word map reduce you might get. Okay, just tell you which document contains the word 100%. What augmenting means: to augment the computation, you slightly change what the mapper and reducer emit, so they also include the position the word offset within the document. So document id. Okay, so now we, instead of key value pair, we are still returning key value pair, but the value here is now a tuple. Not tuple, basically a dictionary, or basically two value output. Okay, yeah, my mic was gone also. And map appears 5 and 42 doc emits. Okay, map reduce 5. Okay, so now this is offset, I guess. Yeah, it's easier to think like offset. And since we have sorted it, it will come like, okay, first the 5 and then the 42, and MapReduce will take it and it will say, okay, doc for doc, no, what? The reduce output will be word, document ID, and then its position. Yeah. Mm-hmm. So now we can say that reduce the, for each word we will have a value itself can be an object, I guess, and will be a map, and map will contain the word and the list of all the list of all the positions. So essentially previously the map, the output was the list of all the documents, but now it's the map where we have all the documents as keys, and the values of those keys will be the positions and the offset in which it contained in sorted manner. Yeah. Okay, so yeah, now if the word changes, the map reduce automatically will understand that, hey, yes, from 5 and 6 we have a change and we have some new insertion here and there, so it's easier to track everything. Keeping track of word position let you support phrase queries. Example, map reduce next to each other. Yeah. Okay, do proximity search, word near each other. Yeah. Yeah, it's essentially easy to do the proximity searching, because I want to find 6, I just go through each of the map and find 6 really quickly. Also we have, since it is sorted, we can also use binary search, all those stuff. Improve ranking as relevant scoring. Improve ranking as relevant scoring. Yeah, I guess, yeah, we can also use that for somehow. I'm not okay, ranking is okay, ranking maybe, yeah, maybe based on the position and offset we can make it work with ranking. The last line said, with small straightforward change to my reduced job, you can build a positional inverted index, not just a basic one. Okay, what the heck does even inverted index means now? What does means an invert? I wrote inverted index because I forgot to type I, and it's corrected me saying that an inverted index, not inverted. Is it a structure that tells you for each word which document contain it? Okay. It turns out I'm not really good at data structure algorithm. Didn't know about inverted index that way. A normal non-inverted index, you might think document 1 contains a word inside, document 2 contains a word inside. Yeah, that's what normally people think, but not programmers, right? Doc 1, MapReduce is fast. Doc 2, MapReduce is scalable. Document with words, that's a normal way. Inverted index inversion, basically word and document that contains map as yeah. Now you can search for word like MapReduce. You can immediately find all the document that contain. Yeah, inverted index come into core idea behind search engine that okay, this word is being used in this doc, this word is being used in this doc, and if we have a lot of words that are being used, if we have single word, basically a single site that referenced by a lot of sites, that's certainly pushed up by SEO. Yeah, makes sense how that works. Text search in full databases, yeah, easy. A word in a lot of documents, yeah. Full text search engine. Instead of scanning every document, you look up word with inverted index, instantly get the all relevant documents. Yeah, when the paper says set of output forms a simple inverted index, MapReduce is being to use this word list of document large scale. An inverted index like an index at the back of the book. It lists a word and tells you where it appears and not the word number. Yeah, makes sense, I guess. Makes sense. Okay, that was something new, like inverted index. Okay, in all honesty, inverted index is something I would have guessed, but it's good to knowing like how that work. And essentially everything could be guessed in hindsight, I guess. But yeah, it was good to know. And then this thing, right? Where it is, right? This thing I didn't even thought of, right? ChatGPT straight up helped me understanding why it says that we could essentially augment the map reduce a little bit more to get the position of working as well. Completely making sense. I mean, that's why uh, LLM model and Gen AI is sometimes so good, right? It can get you to learn things a little bit more faster. If I would have been trying to find it just via normal Google search, it would have been a little bit more trickier. I would have found it essentially, but it would have been so much easier. Good AI, good chat GPT by the way. Distributed sort, nice. We're in the territory of DSA only. The map function extracts the key for each record and emits a key and record pair. The map function extracts the key from each record. The reduce function emits all the pair unchanged. This computation describes the partitioning facility. Okay, wait, what? What the heck was that? So, the map function extract the key for each record. Extract the key for each record. What is record exactly? And emits a key record pair. So basically we are saying that for each key we are emitting its key and record. The reduce function emit all the pair unchanged. I'm not sure what does that even mean. This sentence is describing a very simple MapReduce job so that it can feel confusing because almost does nothing. Wait, so let me get this straight. This means that I did not understood a single word about absolutely nothing. Okay, I understood a lot of, not a lot of example, but essentially a majority of the examples, but I failed completely on something that described nothing. Fascinating. The map function extract the key from each record and emit a key record pair. The reduce function emit all pairs unchanged. What is record here? Thank God. Record is one unit of input data. Okay. So it's essentially saying that for key value we just emit back key value again. One row of a table, one log entry, one document, one key value entry for a file. Think it of think it think of it as record equal to key value or just the data structured data item. Yeah. Look at each record, extract the key from it, maybe user ID, and emits again the record. Okay. So record is some sort of any kind of input data, doesn't matter. but it will be coming as okay. So it is essentially saying that we are just throwing whatever is being coming as input, right? So suppose you input, for example, a weblog record is basically user this. So this is a complete record. But what would have been the key? I'm assuming key could be something like the URL or something, whatever it is. So we take the map function as like okay, use and record 1, use and record 2, use and record 3. Reduce function, reduce all the grouped for it reduce this and emit the pair unchanged. So what's the point? This map reduce is essentially doing grouping, sorting by key. Group all the records same together, possibly sort them out. Okay. The map tag each record with a key, group records by that key, does not modify them. If you are using MapReduce infrastructure, parallelism, shuffling, sorting, not a combination. Recognize the data without reaching data type. Okay, so it's essentially very easily saying that okay, hey, when we are going to take the record and we are going to just again give it back to you, obviously based on some sort of key, and we are not going to touch that value or that record. You're just going to get it back, but maybe in some sort of organized way that you want. Makes sense, but I'm still not sure what's the key here. So map function takes the key value. Value could be the record itself. What's the key? Maybe key is the same thing, right? It just passes it back. The map reduces, passes the exact input back. But since we have the same input, we have multiple intermediate key value pair, which is essentially the same thing as the input. Basically now reduce will take it also, it will throw it back again without changing anything, but the structuring could have been changed because we might have some sort of sort or some any other infrastructure thing that is different. So oh yeah, it says that it's a distributed sort. Okay, okay, so it essentially is the same thing that GPT is saying, that we take the input. Okay, we can take the key, extract it from the record, or just throw the key value, whatever it is. So essentially we are taking the record and we are not doing anything, we are not changing anything. It's just that since it's coming from map and we are going through reduce cycle, we can essentially have some sort of reorganization or sort. And since it's on a distributed parallel system, it could be said that distributed sort. Oh god, that was that was that was probably the easiest one, but that was the most mind-boggling one yet, because the side effect was not so easy for me to understand from the first glance. Let me just get it once again. But how does this sorting work, right? So yeah, but how does this sorting works? Does user write the sort algo in map/reduce function? Let's see what is it. This is the key MapReduce inside. No, the user does not write the sorting algorithm. The sorting automatically by the MapReduce framework between the map and reduce. But here it says that where it was in the, yeah, it should be inverted index sort the. Says that the sorting also implicit by the framework. Let's think. MapReduce concept should 3 stages. MapReduce, sort and shuffle. Okay, so that should be sort and shuffle. Shuffle and sort is part of building the system. This list of key value reduce output. What the system doesn't, you do not code this. Collect all the map out group by key values. Sort keys and send it. Okay, I guess so it does sort it, and I think we can also set what kind of sorting we want. The reduce is called once per key and receive all the values together. Data is partitioned by key hash or range counted within partition. Okay, can you control the, yeah, that's my next question. Can you use the control the sorting? Yes, but indirectly you can customize key. Okay, custom comparator, yeah, we can provide comparator. This means we can control sorting, I guess. Partitioning, okay. Mm-hmm. Okay, yeah, yeah, I mean, famous sort by key, not by value. So here in this we have essentially sorting one key. The computation depends on the partitioning facility described in 4.1 ordering. Okay, so yeah, they will describe 4.1. Okay, that's good. That's good to understand. That's really good. We also have a couple of questions of fault tolerance, but yeah, that will have to wait one second. Okay, the third part is pretty damn big. Okay, I think the third part will probably take me 2 tries to complete it. Okay, but I think I think that wraps up the today's video, right? Basically, today we completely understood what the programming model is, which is essentially this, right? Then we also understand what's the example and what basically is the interface of this particular MapReduce model. We learn more about the examples like counting frequency in distributed manner, distributed grep. We also counted the URL frequency, also how we can create the reference reverse web link graph. We also understood like the term vector, the most important words count per host name. We also understood what inverted index is and how we can actually track down the position in much more efficient manner when it comes to inverted index. There's also distributed sort, which is essentially using MapReduce infrastructure to do some sort of sorting. And this was really cool because this was not about the business use case, but it was more about the infrastructure and telling us how a MapReduce infrastructure is built that way. So that's good. That's good. Okay, I think that's it, right? Like we have the third part as implementation, but we will do it in next part of the video. All in all, this was a good. This was a good. This I think this was a good session. Okay, I won't talk much. I have yapped a lot in this video, so I will keep it short. The outro. Anyways, hope you have a good day or good night wherever you are, and what I don't know, and stay healthy and do your best. Peace out.